Alright, so today we are going to be learning about atomic spectra. Woohoo! We gotta get excited like this guy. Anyway, it's all going to start with an atom absorbing energy and getting excited. It will then emit its energy in the form of light, and that energy will be seen as different colors based on wavelength. As you can see here, each element has a unique combination of lights and is called its atomic spectrum. This kind of acts like a light signature for each of the different elements that we know of. Here are examples of just a few, like mercury, neon, hydrogen, and helium. Pretty cool, huh? Some of the things you saw during the intro of the video were atomic spectra of certain elements. This is what we will be learning more about today. That was a very quick overview, but to get a better understanding, let's dive into some history. The founding fathers of atomic spectra, so to speak, are Max Planck and Albert Einstein. Planck said that energy was limited to certain values and increases in little jumps. These little jumps are called quanta, and the word quantum is singular. Einstein further explained that energy comes in packets, which he calls photons, and this helped explain what Planck said about energy. We can see that instead of rising steadily, it sort of had steps that it would experience because the packets of energy would either be received or lost, and energy would go up or down in increments rather than a slope. To provide an illustration of this concept, we can see that electrons can only exist in certain spaces around the nucleus. These areas we call shells. This is what Planck meant by energy being limited to certain values. For example, let's say one of these electrons is floating around the nucleus in its orbit, and along comes a photon, or a packet of energy, and the electron absorbs it. We see that it moved from the lower energy shell to a higher one. You can see that I have labeled these shells N1, N2, N3, etc. N is the quantum number or relative energy state, 1 being the lowest. In order for the electron to move up or down, it has to encounter a photon that matches exactly the amount of energy needed to go from one level to the next in either direction. For example, we can see this other electron circulating. It must emit a packet of light with exactly the same amount of energy that it needs to lose in order to go down to the next level beneath it. It is this constant absorption and emission of photons, or packets of energy, that releases light at certain wavelengths and energy levels to produce the colorful spectra we can see. I have drawn another diagram to the left to show it kind of as an energy funnel with different steps to show the difference in energy. This isn't the actual shape of the shell, but hopefully it can be another way to look at it and illustrate an increase or decrease of energy. Remember, different amounts of energy have different wavelengths and therefore have different colors. If we go back to the top again, here's an example of atomic spectrum for different elements. You can see how different each one is, and it's because of the different quantum numbers and energy levels. And because of that, different wavelengths are required to each of the levels, producing different colors. Now I'll explain what you need to know in order to solve some problems. Here's the equation we'll be using, and it helps us to determine any one of these variables, whether it be which level electrons are falling from or jumping to, or what the wavelength is for something that jumps from, let's say, from level 3 to level 5. First off, we will describe lambda. Lambda stands for wavelength, or how long the wave is. This is important because, as mentioned before, we see different wavelengths as different colors. Here is an image of the visible light spectrum. You can see that red has a long wavelength and purple has a short one. Something good to know is that as wavelength decreases, energy increases. We also have the Rydberg constant, which is represented by the letter R. This is equal to 1.0973731 times 10 to the 7th meters to the negative 1. N stands for shell number. Ni is where the electron was initially, or is initially, and Nf is where the electron finishes, or what its final spot is. So now that we have gone over some history and basics, let's see how much we understand. We'll start you off with some easy questions and then work our way to the one that requires us to use the equation. Question number 1. What is an atomic spectra? Is it A, a light signature or combination of colored bands produced by an element dependent on its unique energy levels? Is it B, a new superhero who wears glasses? Or is it C, a spell that allows you to see the world in gradients? You got it right. The answer is A. Next question. What does quanta mean? A, the new dance move created by those in quarantine? B, certain and limited steps that energy can exist in? Or is it C, a new flavor of Fanta soda? Hopefully you got B on that one. Next question. What is a photon? Is it A, packets of energy? Is it B, the name of Optimus Prime's camera? Or is it C, a slang term used by teenagers nowadays to describe a quick photo shoot? You got it right again. The answer is A. So next question. The atomic spectra for hydrogen and neon are the same. Is it true they are both elements that we know of, so they will have the same appearance? Or is it false, because each element spectrum is unique, like its own light signature? It's false. Last question, before the one that requires the equation. The energy in a photon that is emitted or absorbed needs to be the exact amount needed in order to drop down or jump up in energy level. True, energy can only exist at certain levels, so the energy in the photon must be exact. Or false, electrons don't play by anyone's rules. They can do whatever they want. So hopefully you picked true on that one. But good, hopefully you did well. Now let's get to the hard one. Here it says, a wavelength of 4.653 micrometers is observed in a hydrogen spectrum for a transition that ends in n equals 5 level. What was the n initial for the initial level of the electron? So we're going to write out our equation, and we start with the one that we talked about earlier. And we will begin to arrange the equation since we are looking for n initial. So once we have isolated the n initial to one side, all we got to do is start to plug in the values that we know. In this case, we know lambda, and of course we know the Rydberg constant. We continue to go through the math, and we end up with the answer of 7. This means that the electron was originally at level 7, then a photon with a wavelength of 4.653 is emitted from the electron. This is the precise amount it needed to release in order to drop down to level 5. So that's one example of how you can use that equation to figure out problems that pertain to atomic spectra. Hopefully, you have more of a grasp of what atomic spectra is and how it came about. So to recap, it is a light signature of an element and is produced by atoms absorbing and emitting different amounts of energy, producing different colors. It is evidence that quantum mechanics is true because it shows that energy comes in little pockets called photons and that they can only exist in certain limits and steps. So thanks for tuning in. Until next time, the end.